So hello everybody and welcome to this other Thursdays at BRiAS seminar event. So also today we have two very interesting seminars. So the first one will be from Professor Alessandra Parisio from the University of Manchester. So I know Alessandra since my very first year of PhD because we started more or less at the same time in two universities not far away. So for years we were crossing each other at events, conference, and so on. And now with BRiAS we had finally the occasion to spend a little bit more of time together and to work. So Alessandra is an expert for what concerns the use of model predictive control and optimization-based control in general on electrical networks. So she will present us something in this field. So without wasting too much of your time, I will leave her the stage. So please, Alessandra.
Thank you Thank you very much, Emanuele, for this opportunity. It's a real pleasure to be here. What I would like to discuss with you today is some work that we have been doing within some national UK and EU projects dealing with how basically to manage and control an arbitrarily large number of flexible resources that we expect more and more to find and to have available within our energy networks. So this title is quite general, but basically the plan is to set a little bit the context and then give you just a very brief overview of a couple of these optimization-based control of flexible resources in different time scales, and then to detail one of them a little bit more. Basically, as all of us know, we are witnessing a paradigm change within the energy network because of the increasing penetration of renewable energy sources, which of course pose challenges to the inertia and the stability of the electricity grid, and also the decarbonization or the electrification, which is more correct to say, of the other energy sectors like heat and transport, increase, of course, the stress on the electricity networks. One promising direction, as probably many of you know, is to try to unlock the flexibility that will be available, especially in the distribution energy and in distribution electricity networks. So at lower voltage levels, where basically our homes and industrial facilities are connected to, of course, electricity systems have always been flexible. You need flexibility because you need to meet a time-varying demand, electricity demand. But of course, the challenge here is that the demand side becomes much less predictable, and the more that changes, the rate of change in the demand is much faster because we have generation also, distributed generation also located at lower voltage levels. So we need more and more flexibility resources to be able to keep the light on, basically. And some of these flexibility resources that we expect to become more and more available are, of course, storage devices, especially batteries. I know there are much more expert than me on this here, on these assets. And here the idea, we treat batteries more on a system level perspective. So we consider that there are batteries that can be located at different voltage levels and also at residential and commercial levels. And the idea is, of course, that they are small, they have very small capacity. And in order to provide a system level response, you need to synchronize their response and aggregate their response at each point in time. Then this aggregation of storage devices, we can call it virtual storage plants. Virtual because they are not virtual, they are not physically a large-scale device, but they represent virtually a storage device that can be controlled optimally in order to provide the required response when the operator requires that. And then another interesting additional source of flexibility can come from the fact that there are, in our cities, for example, we have multiple energy vectors that interact. In our homes, we use not only electricity, but we use heat, we use gas. Therefore, buildings itself can be seen as a multi-energy system. So the focus here is on the energy conversion aspects and on the different time scales of the various dynamics. So electrical dynamics are much faster than thermal dynamics. So, for example, as a classical example, if you consider heat pumps that basically use electricity to produce heat, or you have refrigerators, if you just turn them off for a few seconds to help with the frequency, that does not impact at all the thermal comfort of the building occupants, so that can be done. And this is about, to give an idea of how flexibility, due to the interaction between different energy vectors, can be used to provide flexibility and sustain the grid, the network operation. So the motivation of this studies is, as I mentioned, to try to explore the potential contribution of these flexible assets to support a more sustainable grid network operation. And in order for these assets to provide an adequate level of service, we need to coordinate a potentially very large number of them. Could be even millions in the future, as is expected. So this brings, of course, coordination challenges because the grid conditions are highly time-varying. There is high volatility, and this asset needs to be dynamically responding to these changes. And sometimes, for some of these services, there are very strict time requirements, and this brings further challenges. So the idea here is to explore and design optimization-based control strategies, because, of course, we want to do this aggregation and coordination in an optimal manner. But these frameworks need to have some properties. Local computational burden because of the strict time requirement. We might need not to share private information, and we need to meet the service requirements. And the control design should be as flexible as possible, because we might need to accommodate different criteria, optimization criteria. So now I will give you just an idea of some of these optimization control frameworks for coordinating different types of flexible resources on different time scales. For example, this is one example of a work that we have done within a UK project. So we consider an urban district where you have buildings, of course, and buildings in themselves equipped with batteries, heat pumps, solar panels, and so on, and and controllable loads. They can be seen as multi-energy flexible resources. And, but of course, we have to consider that these buildings are connected by networks. So they interact through networks, they exchange different power flows, electrical and thermal power. And the network model needs to be considered, both the electrical network model and also the thermal heating and cooling network models. And the problem, if we want to optimally coordinate the energy management of this large-scale system with several buildings, of course, it's a huge problem, also considering that we need binary variables, because you have resources that can be turned on and off, so you need the binary variables to model that, or you have battery that can charge and discharge, and so on. So the problem becomes, if you want to simply optimize the energy, minimize the energy costs and the interaction with the main grid, the problem becomes very big. And it's basically, if you want to apply model predictive control to this problem, and so try to obtain at each point in time, for example, at each 15 minutes, an energy plan over the next day, it's basically impossible to solve it by using off-the-shelf solvers like Gurobi or Cplex. For this problem, then, we applied a decentralized approach, where basically you have a local problem solved at each building level, and then you have an energy coordinator that takes care of the network to make sure that what the building decides does not have does not impact the network operation. And we apply this dual subgradient algorithm with adaptive constraint tightening. Basically, is to make sure that if the building, the local energy plans are such that the constraints on the network are not satisfied, the buildings are asked to modify their required energy profile. And we did that because we at least could have feasibility guarantees. So we can make sure that the energy plans can satisfy also the network constraints. And we got significant reduction of the computational times with respect to a centralized approach. Up to 3 orders of magnitudes is a huge difference in times. And that allowed us basically also to increase the horizon. Just to give you an example, to solve this optimization problem, just considering 3 time steps ahead. So if one time step is 15 minutes, so we can look ahead by 45 minutes. And the type of control law that you get by using such a small, short horizon is not very effective. Looking more ahead, so having an idea of the future energy prices, for example, for the overall day ahead, can help you obtaining an energy plan that is more cost efficient, for example. So by reducing the computational times that much, we were able to extend the prediction horizon till to 48 time step ahead, which could also yielded also to more significant cost reduction. Then, of course, I will be very happy to discuss and give you the details if you are interested on this type of approach. Then this decentralized MPC worked well for services and energy management problems that work on longer time scales, as I mentioned, 15 minutes. But it does not really scale well because anyhow you have binary variables. And if we are interested in other type of services like frequency services or voltage control, where the time scale of the service requirement are much shorter, like seconds, or even less than 1 second, that that cannot work well. So when we wanted to look at the coordination of, for example, storage devices, so to provide support for the frequency, system level property, that is the frequency, or the voltage, and make sure that the electricity network works, the electrical network works well, we explored other type of methods, in particular online optimization. I know that there are experts on this as well here, so I'm very happy to have further discussions. And then we started exploring this online convex optimization, again in a distributed setting. The nice thing of this approach is that it's not an iterative approach, because we don't have time to wait for iteration until convergence at each point in time, at each time step. So the nice thing is that you solve again a time-varying optimization, an optimization problem over a given prediction horizon. But you basically are able to compute a control input at each sampling time, in this case 0.1 seconds. And of course, you allow some violation and suboptimality at beginning until convergence, basically. So the fact that this is not an iterative approach helped a lot when it comes to frequency and voltage control, for example. And here the idea is that within this OCO framework, you have an agent, which is the battery system, for example, that chooses a strategy, which is charge, discharge, by how much power. And it suffers a loss because you have to make a decision now without knowing what the other agents do, and without knowing what would be the best, because you don't know the disturbances. Then you suffer a loss, and you can basically mathematically formulate the regret function, which gives you an idea about how much you deviate from the optimal or the best decision in hindsight. And the idea is to have this regret function going to 0 as you learn more about the interaction with the environment. Then, of course, we could prove that by applying this method, we achieve a sublinear convergence of the dynamic regret and fit. Basically, the dynamic regret gives you an idea of how well you are doing about the performance, and the dynamic fit gives you the idea of it quantifies the constraint violation, in this case, the power imbalance. And it scaled very well, and we could also track a time-varying voltage profile, for example, at the grid interconnection point between distribution and transmission networks. So it works very well on simulation. But the point is that we could prove only the asymptotic convergence, so we don't have some guarantees that within a required time we have convergence. So this brings me to the convergence rate is insufficient for very fast frequency response services. And this brings me to the framework that I would like to detail a little bit more and talk to you a little bit more about. And the focus is on these fast frequency services. And just a very, very brief overview is these are type of services that basically the main feature is that you need to provide a response within a given time, and it's usually 1 second or 2 seconds at most. These are being launched and tested worldwide, and also in the UK. We have these three types of fast frequency response services, which are dynamic containment, dynamic moderation, dynamic regulation. Basically, dynamic containment is to recover, is a post-fault service, so is when a fault happens. For example, there is a huge power imbalance somewhere in the network. You need to call the batteries for this, for helping recovering from a frequency loss, a frequency drop within a given time. Dynamic moderation, dynamic regulation are continuous services or more dynamic services. They are pre-fault, and they are and the objective is to prevent basically deviation that are small and still acceptable from escalating more. And just to give you an example of why these services are important and are being explored. For example, we had in the UK in 2019 a huge blackout with, I think, if I remember correctly, 1.9 gigawatt of generation loss because of lightning. And actually, the problem with the integration of renewable energy sources is that they make the rate of change of the frequency faster, which means that you have less time to stop the frequency from dropping or rising as well, and less time to recover. And in this case, for example, a great help came from the batteries, because batteries are able to provide the required response in very, very fast time. And this helped a lot. And this speeding up, this 0.16 hertz per second is a very fast frequency rate of change of the frequency. Basically, the frequency went out from of the statutory limits in less than 10 seconds. So you have very little time. And spinning reserve, so our gas turbines or conventional generators, this with the rotating machines, cannot help within such short time. So in this basically is just to give you an idea of the type of service requirements. So it's important to know here that the maximum time to delivery is 1 second in case of dynamic containment and dynamic moderation. And dynamic regulation, we have a little bit more time. And there is also a minimum time where you for the delivery duration, for sustaining your response. And this is to give you basically the delivery requirement curve for the three types of services that we wanted to focus on. Basically, they are piecewise linear function. So this is the frequency deviation. You have a dead band when the frequency deviation is so small, between plus minus 0.015 hertz. You don't have to do anything. But when the deviation starts to become bigger, then this is the slope of your response, basically. So you have to satisfy this delivery requirement curve. Of course, the saturation point depends on the capacity of the battery. So you have a contracted quantity with the system operator, and this, of course, all depends on the contracted quantity. And as I mentioned, is about aggregating the responses of multiple assets. And we call this aggregated response unit to provide a coordinated frequency response. And in this figure, in the top right, is again just to give you an idea of how how can vary the frequency, basically. So it's highly varying and volatile. So the challenge, there are a few challenges in trying to optimally coordinate these storage devices for providing this type of frequency. The strict time requirement, as I mentioned, so we need a time limit on the convergence to the optimal trajectory. And we don't have time for iteration, so it's not an iterative approach. We have to, of course, the optimal trajectory evolves dynamically. We have to consider the time-varying grid condition, and the framework has to be scalable because in the future, as I mentioned, we expect many of these devices to be coordinated in order to support the grid. And so far, we actually managed to, by using online convex optimization and inspired by the output regulation theory, we basically managed to develop a control framework that is can guarantee fixed time convergence, and it's based only on measurements, so on the frequency deviation measurements. This is the information that you need to have. And it scales sublinearly. We tried, I will present first the centralized approach, but one of the requirements is also that this is amenable to a distributed implementation, meaning that basically, each battery system performs their calculation. They exchange some information within a neighbor, with a neighbor, with some neighbors, some other storage devices in a local communication network. And then, of course, it's easier because it takes less time in theory, because the calculation is performed. There are calculation performed in parallel. Now, the other problem with the standard online convex optimization that I talked before is that it's mainly optimization, does not really consider dynamics, and we have dynamic systems, so we have some dynamics to consider. And this is the dynamic model of the battery system or the storage system that we consider. In particular, we focus on the batteries. This is very simple, can be found in the literature. It's based on circuit theory, basically Kirchhoff laws. The idea is that we have a battery management system that gives an operational baseline. We consider a constant operational baseline, but the algorithm can handle also time-varying operational baselines if needed. So the battery management system takes care of what is the best operational baseline, the best power that has to be considered. But what our actual decision variable is how much we can deviate from this operational baseline in order to provide the required level of service. So this is our decision variable, which is also the state of our dynamic model. We consider also the inverter that is, of course, needed in order for the battery to be interfaced with the grid. So this is our power, and there is also that we are also to consider. So we consider the dynamics of the power, that is the deviation from the operational baseline, and we also consider the voltage and the terminal voltage of the inverter, which is basically the input to this. The pulse width modulation generator here. So as I mentioned, basically the decision is based on the frequency measurements, and the other information that we need is the required contracted quantity with the system operator. The model can be basically formulated, expressed in this simple way. This is a second order model. As I mentioned, the state here is the deviation from the baseline. So we are interested in the power in this power dynamics, and we also consider the voltage, the terminal voltage of the inverter for voltage control. If the dynamics of the inverter are very small in the simulation, we found that, for example, if this is the time constant of the inverter, if it is smaller than 100 milliseconds, basically we could not observe any difference by considering a second order system or a simple first order system, because if we neglect the inverter dynamics, basically this reduces to a simple first order linear system. So this is the model, and this is the frequency varying optimization problem that we consider. So basically we want to minimize a cost function, which could be anything as long as it's strongly convex and differentiable, continuously differentiable. We need that for proving the convergence. And is a function of the frequency deviation of the power of the power. When I say power, it's always the power deviation from the baseline. And it could be a cost function. We could include degradation of battery system, depending if it can be formulated as a convex, strongly convex function. Then this is a very important global equality constraint. Of course, we want that all the responses from the batteries meet the contracted service according to the service delivery curve that I showed you before. And we also have local feasibility sets to consider. Each battery system has some limitation, operating limits, which could be set by battery management systems. Here, as you can see, the bounds are constant, but again, we can handle also time-varying bounds. So this is the problem, and as I mentioned, with the standard classical OCO, it doesn't work well. So we basically design adopted an approach which is basically control-oriented OCO, where we took inspiration from the output regulation in order to, of course, track a time-varying optimal trajectory. And we basically designed a dynamic system, which is the battery system model that I showed you before, whose states, which also represent the decision variables of our optimization problem, converge to the optimal solution. The optimal solution, the optimal trajectories, which are depicted here as an example, so they are unknown, but we could estimate them based on the derivatives of the KKT conditions derived from the optimization problem. And of course, there is some time that is required for reaching the convergence. So our decision variables initially will deviate from the optimal trajectory, but by using our control law, which includes a feedback term and a feed-forward term, it converges after a while to the optimal trajectory, and it will, in optimal trajectory that is time-varying because of the frequency dynamics are time-varying. And we also have to consider that there are local feasibility sets, so operating limits that we have to consider. And this also means that the optimal trajectory, when and if the boundary of the local feasibility sets are reached, that it can change. and this has to be considered. So we included a switching state-dependent switching signal in order to account for the boundary and make sure that the local feasibility sets are considered, which is not commonly done, and it was also the challenging part of the control design here. So the local feasibility sets are always met, so we don't have to wait for convergence. However, the global equality constraint that I showed you before is met only when we converge. So we have initially, we can have some violation of the contracted quantity. But if we converge within the required time, that's okay. So as I mentioned, basically the structure is a feedback and a feed-forward term. The feedback term include a projection operator when you reach the boundaries to make sure that you are always within the individual trajectory of the storage devices are within the feasible, local feasible sets. And we include the feed-forward terms that basically drive the trajectory of the individual assets toward the optimal trajectory because they are based on the derivatives of the KKT conditions. So the optimization problem is then reformulated as a control-oriented problem, which is basically the tracking of these optimal trajectories. And we consider two problems depending on whether you have a first-order system, so you neglect, or whether you or not you neglect the inverter dynamics, so whether or not you have a first-order system or a second-order system, which complicates a little bit the control design of the feed-forward terms. And as I mentioned, these are the main variables. So you have a control input to the voltage controller as U. The reference signal, if we consider, the reference signal to the PWM generator, and then X is the delivery quantity, again, the difference with from the baseline. Now there is some math because the derivation of the feedback and feed-forward terms seems a little bit complicated because of the time derivatives of the KKT condition, so I won't bore you with details, but just to give you the high-level description, as I mentioned, of how the design has been done, we have again that the estimation of the dynamics of the optimal trajectories are based on the time derivatives of the KKT conditions, and based on these, we can derive the feed-forward driving terms for the first order and the second order systems, but for the second order system we need to differentiate twice, so we have a little bit more complex design. And as I mentioned, in order to consider the boundaries that the optimal trajectory can be different from when the boundary of the local feasible sets are reached, basically we had a state-dependent, not time-dependent, a state-dependent projection operator that is synchronized with the activation of the projection operator. So basically, when we are within the feasible, local feasible sets, we consider that the feed-forward terms, and we don't use the projection operator within the feedback term. When we achieve the boundary, when we achieve the boundaries, basically we don't need the feed-forward term, but we include a projection operator in order to make sure that we are kept within the local feasible sets. And then if we consider, this is for the first order system. For the second order system, as I mentioned, the design of the Feed-forward terms are a little bit more complicated, so as you see here, we need 4 of them because we have to differentiate twice because we have second-order system. And then, as I mentioned, we have feedback laws for first order and second order system based on primal descent and dual descent, and how we basically also need to include an error term. And this error basically gives you the measure of how far you are from the optimal trajectories, and the main control objective is basically to drive this error term to the origin within a fixed time. And this is what the control inputs do. That the control policy drives the error term to the origin within the required time. And when the origin is achieved, you solve also the optimization problem. And then, of course, you have also these feed-forward terms to enable the tracking. And based on Lyapunov arguments, we could prove also the fixed time stability. So the convergence time, in theory, is upper bounded by this term, where you have these gammas that are basically tuning parameters. However, you cannot tune them and set them too large in order to have a very, very small time, because otherwise you might violate the boundness assumptions on the time derivatives. But for the problems that we considered, it was fine. It worked well. And I don't know how I'm doing with time, if I have time. Then just a few simulation results, just to give you an idea. And the plan is also to move to a more experimental environment to see how this work in a more realistic environment. So we considered first a simple case just to see how the control framework works. In a transmission system here, with 14 bus is a IEEE benchmark validated with 6 storage assets. You can see them here located different buses. And the local cost function includes basically is consider the costs of the service of the battery systems, and also include the electrical distance between the assets, which is important especially for the dynamic containment, because the distance from the fault location is important in order to incentivize the storages that are closer to the fault location to provide more, to support more, to contribute more to the service delivery. And then, for the dynamic containment, and I remind you, dynamic containment is a post-fault service. So when there is a major fault, the batteries are called by the system operator to support the frequency. And you can see here at time 20 seconds that there is a major, there is a step load change, and then the frequency, so the load decreases suddenly by a large amount, and is, I think, 300 megawatt, and the frequency starts to drop, and the batteries are called, they provide the service, they stop the frequency to drop, and the frequency starts to be brought back to the nominal value, And then also the other assets, the synchronous generators, of course, start to provide their services, and the frequency is recovered, basically within short time. And here it shows the power delivered by all the batteries. You can see that some of them, the battery 1 and 6 here, they reach their operating limits. But this doesn't affect the service, the contracted quantity, the service delivery, so that worked okay. And here you can see that the convergence is basically achieved. This is the very small deviation, and the convergence is achieved in half a second. And we set a upper bound on the convergence time as 0.7 seconds. So that also worked fine, both when it concerned the optimality and the feasibility. And then we also tested the dynamic regulation, which is a pre-fault service. And basically, we injected continuous net load variation. So it's not a step load change, but there are continuous net load variation. So you can see that the frequency varies a lot. And the batteries, of course, always according to the service delivery curve, they provide the required service. Again, the convergence is always achieved in half a second, so it's within the time. And we also, in order to have an idea of the optimality and the feasibility until convergence, we calculated, because of this, the fact that there are continuous net load fluctuations. We consider the root mean square error between the actual cost, so the optimal cost, versus the actual cost, the cost of the batteries, and also the delivery response against the contracted quantity. And you can see that the errors are kept quite small, so that is acceptable. And the last thing is we try to test the scalability of the control framework. So what I presented, the simulation results I presented so far concerns the centralized approach, but we wanted to see how it works in a distributed setting. And I will not give you the detail, but basically we added a step for a consensus step to reach consensus on the global equality constraints, basically on the contracted quantity. And again, fixed time consensus, so that the algorithm remains fixed time convergent, but you have to include the consensus time. There are not nested iterations. It's, again, non-iterative algorithm. And we can see that although the centralized approach with an increasing number of assets, although the centralized approach, the computational times, the average computational time per control interval, and each control interval is 1 millisecond, is, again, very small. The distributed is smaller and is scaled sublinearly. So if we think of implementing these for millions of storages, this can help. However, we have not included the communication delays. We have not explored the communication aspect, so this is part of future work. Thanks for your patience so far. And just to mention some of the future works, as I mentioned, we tested this in simulation, but at Manchester we have the real-time digital simulator, which can be interfaced with a real storage battery and also with microcontrollers. So we are planning, and we just started to test this on an experimental setup which is more realistic than just MATLAB and MATPower. And then we wanted also to consider the stacking of the services. So far we consider only single individual services, but in the future, not already now, distributed system operators and also battery owners are very interested on the possibility to provide multiple services at the same time or one after the other. So horizontal, vertical stacking of services, seems to be of interest. And considering also multi-energy assets like pumped thermal electricity storage systems. And also, if the asset modeling becomes more difficult, so we already, with the second order system, as you might have seen, the control design for the feed-forward terms was already more complicated. So if the model, if the dynamics of the assets are more complex, this might make the design, the control design, more difficult and maybe not possible to run on low computational units. So we wanted to explore the combination with reinforcement learning, safe reinforcement learning. And that concludes what I wanted to talk to you about. Thank you for listening, and I'm happy to take questions. Okay.
So thank you, Alessandra, for your talk. This is the typical level of complexity when you go for real problems. You need to use multiple techniques at the very same times. So it's thank you for this nice overview on this. Are there questions from the audience? On batteries.
Of course. Oh, I have.
No, me.
Yeah,
me.
Thanks, Alexandra, for your amazing presentation. I have a couple of questions. The first one is regarding the first example, in which you have many households and you have this cooperative policy. I was wondering whether we can include, or we are considering there, a priori knowledge of the grid. We know that we have 2 peaks of demand of electricity during the day, and at those points, for instance, the household batteries, they will do the so-called peak shaving or other many techniques to reduce the consumption of the client. So if we don't have industrial services within, that can be considered within that policy.
Yes.
Are we considering it?
Yes, we can. The periodicity in the demand, yes, definitely it can be considered. It can be included in the within the MPC. You need to forecast some of the aspects of the problem that you don't have much control on, and so yes, you can include this. But you mean including the demands, the demand profiles from the households?
Indeed, the household profile, and also who is managing that, because usually is the battery management system or the energy management system of the household taking care of that peak shaving,
yes,
or
yes.
is this centralized policy?
Yes, it can be included. Here we basically, the demand from the household is derived from running the MPC problem. And it's all together, basically. So the battery, in the same problem, we include the model of the battery, considering charging and discharging is a very simple model. It's basically a discrete time integrator with hybrid dynamics because you have charging and discharging. And you have a power balance, so if there are other demands, other loads, this is included in the power balance and indirectly within the model of the battery. But one of the requirements is to have a flexible control design, so the problem can be formulated also differently. Yeah, because in this case we have non-convex discontinuities. Is a very complicated problem, so additional complication would not hurt much.
Okay, thanks. And the second one is related to the second example.
This one?
The frequency recovery. The recovery after a frequency drop. I was wondering, in that case, you are assuming that your stationary battery pack has all the power. At some point, we can see that there is a saturation at the highest discharging rate. Yeah. But what about, I think that you link it in the concluding remarks, what about if you are recovering after a second fault and you don't have the energy stored in the batteries to recover after? You will saturate at a certain discharging?
Yes.
So
you consider the initial kind of state of charge. But the idea is I think that this is considered by the system operators, that they know that batteries have, of course, limited capacity and they need time to recover. So probably the batteries are not cold if they didn't have time to achieve at least 80% maybe of the final capacity. So yes, this can be considered.
Thanks.
Thank you.
Okay, thank you, Alessandra, for the nice presentation. I really have just a short question about the second example. I think it was around slide 15, I guess.
15?
Yeah, it was with the optimal, over there.
Yes.
Just to see, because I think I didn't understand. So you compute the optimal trajectory offline, or you recompute it based on what's happening on the grid, or?
Everything is calculated online. There is not any offline calculation. Yes. And is based on measurements of the frequency deviation. So this is the information that basically tells you what is happening. Is all they need to know. The frequency deviation, the frequency deviation basically, and the contracted quantity.
Okay, so that means that at each sample time you recompute the, okay, thank you.
Yeah, and then the idea is that you have this optimization problem. You can write down the optimality conditions. So you have all the functions, and you differentiate with respect to x and lambda, which is the dual variable that takes care of the global equality constraint. And that gives you basically an idea of the direction of the optimal trajectories. And you repeat this at each millisecond. Now repeat, you do that.
Thank you.
Thank you for the presentation. Just to make things clear for me, you solve the MPC problem at each instance, even for frequency, to solve the frequency issues? Each time
we don't care about frequency here, or about voltage. It's just energy management. It's just the power flow exchanges. We assume here is like you have a hierarchy of different controllers that work at different time scales. So at faster time scales, we consider that everything is taken care of. Here we just consider the steady state equations for the networks. And so basically, this is a very good question. Thank you, because I forgot to mention that here in this problem, the dynamics that we consider are the battery dynamics and the thermal dynamics in buildings. So it's slow.
Okay, thank you very much.
Okay, so if there are no other questions, I would like to thank again the speaker. Thank again, Alessandra. And as usual, we have now a coffee break for which we can relax a little bit, and then we will come back here for our second talk that will be on ChatGPT and its use in medicine, as far as I understood. So see you in 15 minutes around, also for the people that are online. See you later.